This video is on simplifying and combining radical expressions. Right, so we're first going to talk about writing radical expressions in simplest radical form. Let's look at some observations, and then we're going to state a property. The square root of 36 is 6, right? Because 6 times 6 is 36. But we could also write 36 as 9 times 4. And then we could separate it into two separate square roots, the square root of 9 times the square root of 4. And then the square root of 9 is 3, and the square root of 4 is 2. And 3 times 2 is 6, the same answer. So what we're doing here is we're trying to say that we could rewrite the square root of a radicand into two separate square roots. Square root of 100 is 10. We could separate that into the square root of 25 times the square root of 4. The square root of 25 is 5, and the square root of 4 is 2. 5 times 2 is 10. This also works for cube roots. Actually, any nth root, a fourth root or a fifth root. The cube root of 216 is 6. But we could also write 216 as 27 times 8. And the cube root of 27 is 3, and the cube root of 8 is 2, and 3 times 2 gives us 6. Okay, so that just kind of shows us that we could separate it into a product of two square roots, or two cube roots, or two nth roots, depending on whatever the index is. Okay, so far we've been simplifying radical expressions that were perfect squares if it was a square root, or if we had a cube root as a perfect cube. Now we're not going to have a perfect square for a square root or a perfect cube for a cube root. You know, for example, square root of 25. The square root of 25 is 5. 5 times 5 is 25. Because as you can see in our example, we're going to try to work out the square root of 40. And 40 is not a perfect square. Okay, so here's our procedure. Write the square root as a product of two square roots where one of the radicands is the largest perfect square that divides evenly into the original number. Then replace the square root with the whole number it is equal to. Leave as multiplication. So examples of perfect squares are numbers like 1, 4, 9, 16, 25, 36, 49, etc. Okay, and actually 1 is a perfect square, but 1 is not going to do us any good. Because 1 times 1 is just 1. And 1 times anything is that same thing. Okay, so we're going to use this property that the square root of a times b equals the square root of a times the square root of b. And a is the largest perfect square. So here's our example, square root of 40. We're going to try to separate it into a product, and one of the numbers has to be a perfect square. So here's our factors of 40. There's 1 times 40. Okay, so 1 is a perfect square, but it doesn't do us any good. So forget about 1 times 40. 2 times 20, 4 times 10, and 5 times 8. Which one of those pairs has a perfect square in it? Right, the 4 times 10. So we're going to rewrite this as the square root of 4 times the square root of 10. Okay, so the largest perfect square is 4, so we're going to rewrite it using the 4 and 10. Now we're going to place the 4 with 2, because the square root of 4 is 2. And the square root of 10, there's nothing we could do with that. Actually, we should think about that 10 doesn't have a perfect square in it, right? 10 is only 2 times 5, and neither one of those numbers is a perfect square. So we're going to replace the square root of 4 with 2, and then bring down the square root of 10, and you're all done. On your Casio, if you have a Casio, or some TIs, Texas Instruments, you could probably just type in square root of 40, and it'll give you 2 square root 10 automatically without doing this. We still want to learn the procedure because it's not going to do it. At least at the time of this video, the Casios are not going to simplify the cube root of 40, or any cube roots unless it's a perfect cube root, or a fourth root or a fifth root. So we need to learn the procedure. Also, we're going to add variables to this expression. And at this time, we probably can't just put that into our calculator. So we need to learn the procedures. Okay, let's work out a couple more. The first one is the square root of 72. First, we'll list our factors. 1 and 72, 2 and 36, 3 and 24, 4 and 18, 6 and 12, and 8 and 9. Now we're looking for the largest perfect square. We need a square root. Let's see, I see several square roots there. There's a 9, right? 8 times 9. The square root of 9 is 3. That's a perfect square root. There's also a 4. Square root of 4 is 2. So far we've talked about 4 and 9. Is there any others? Right, 36. So we want to use the 36 because that's the largest perfect square. So we're going to rewrite it using the 36 and 2. Okay, so 72 equals the square root of 36 times the square root of 2. And then replace the square root of 36 with 6, and we're done. So our answer is 6 square root 2. Not too bad. The trick is to write the factors. Of course, the bigger the numbers get, the more complicated that list is. So not to worry, we have another method that may seem quite easier. After this next example, we'll do that. Square root of 56. 1 and 56, 2 and 28, 4 and 14, 7 and 8. Which pair are we going to use? Right, the 4 and 14. Square root of 4 is 2. So we'll replace the square root of 4 with 2, and then you're done. Okay, here's another method. The last one was a little complicated because we had to find that right pair. This process is more straightforward. Number 1, we're going to find the prime factorization of the given radicand, the tree, the prime factorization tree. Then we're going to circle the pairs. Now, pairs is because we're talking about square roots. If we're talking about cube roots, then you circle in groups of 3. If you're talking about fourth roots, then you circle in groups of 4. In general, if you're talking about nth roots, then you circle in groups of n. Okay, so for every pair, one of the circled numbers will be written in front of the radical. Whatever numbers are not circled stay under the radical. If there's more than one number in front or in the radical, then you multiply those numbers. Okay, so here's square root of 40. What we're going to do is we're going to do the tree to get the numbers. So the tree for 40, we could use 4 times 10, Now, is 4 a prime number? No. So then we're going to break that down again. And then is 10 a prime number? No. So we're going to break that down again. So 4 is 2 times 2, and 10 is 2 times 5. So altogether we're going to have 3 2's and a 5, only the prime numbers. If you didn't use 4 and 10, maybe use 5 and 8. Is 5 a prime number? Yes. Is 8 a prime number? No, we could break that down again. That's 2 times 4. 2 is a prime number, but 4 is not. So break down the 4, that's 2 times 2. So again, we look at how it ends. It's a 5 and then 3 2's. So we're going to rewrite the 40 as 3 2's and a 5. That was the first step. The second step is to circle the pairs. And there's only a pair of 2's. Okay, so for every pair, one of the circled numbers will be written in front of the radical. So a 2 is going to be written in front, and whatever is not circled, well, what's not circled is a 2 and a 5. So a 2 and a 5 will stay inside. Since there's more than one number, we'll multiply those numbers. So our answer is 2 square root 10. Okay, let's try another one. Square root of 72. You might want to pause the video and try to work it out. So, first step is to write the prime factorization. You should get 3 2's and 2 3's. That's the prime factorization of 72. Now we're going to circle the pairs. A pair of 2's and a pair of 3's. So there's a pair of 2's and a pair of 3's. For each pair circled, we're going to put one of those numbers in front. So a 2 and a 3 are written in front of the radical. Whatever's not circled stays inside. There's a 2 that's not circled, so that will stay inside. So our final answer is 6 square root 2. Okay, now we're going to talk about cube roots. First, we'll talk about method 1. This is where we write the cube root as a product of two cube roots, where one of the radicands is the largest perfect cube that divides evenly into the original number. And then we're going to replace the cube root with the integer it is equal to. We'll leave as multiplication. Here are some examples of cube roots. 1, 8, 27, 64, 125, etc. Again, 1 doesn't do us any good because 1 times anything is that same number. Okay, so we want to look at 56. What product can we rewrite it as where one of the numbers is a cube root? Yeah, 8 times 7. So you're going to rewrite the 56 with an 8 and 7, since 8 is a perfect cube. Then we're going to replace the cube root of 8 with 2. So 56 is the same as the cube root of 8 times the cube root of 7. Now the cube root of 8 is equal to 2. So we have 2 cube root 7. Okay, it's a little tricky, right? Method 2, I think most people like. We're almost there. How about 270? Well, we could replace 270 with 27 and 10 because the cube root of 27 is 3. I didn't list all the factors, but if you want to list the factors, it just takes a while. So cube root of 27 is 3, and we have 3 cube root 10. We're all done. Okay, here's method 2. Step 1, find the prime factorization of the given radicand. So do the tree, and then circle the groups of 3. So circle in groups of 3. For every group of 3, one of the circled numbers will be written in front of the radical. Whatever numbers are not circled stay under the radical. And if you have more than one number in front or inside, you multiply those numbers. Okay, these are the same examples we just did previously, but we're just going to do it differently this time. So find the prime factorization of 56. You could use 2 times 28, 4 times 14, 8 times 7. If you use 8 times 7, you might notice right there it's a perfect cube root. So then you might want to stay with method 1. You don't always have to use method 1 or method 2. You could mix. If you think it's easier using method 1, use method 1. If you get stuck, then go to method 2. Okay, so 56, you should end up with 3 2s and a 7. Now we could circle in groups of 3s. There are 3 2s. So since there are 3 2s, a 2 will be written in front, and the 7 will stay inside. 2 cube root 7. Okay, cube root of 270. Maybe you use 10 times 27. So if you get your cube root, you have a 2, 3 3s, and a 5. Now we could circle the groups of 3. There's 3 3s. So a 3 will be written in front, and the 2 and 5 stays inside, which gives you a 10. Okay, we're going to talk about simplifying square roots that contain variables. Let's first put it all together, what we've done so far. Square root of 48. We could either use method 1 or method 2. Here's method 1. We write it as 16 times 3. And then the square root of 16 is 4. So you rewrite it as 4 square root 3. You could use method 2, where you get the prime factorization. There's 4 2s and a 3. So for each pair of 2s, a 2 is written in front. Therefore, 2 2s are written in front, and whatever's not circled stays inside. So we have 4 square root 3. Again, whatever you think is easier. Nobody's saying you have to use method 1 or you have to use method 2. It's always good to know multiple methods, and then you could use whichever one is easier for that problem. Okay, let's talk about variables now. So when we talk about square root of 36, that gives us 6, because 6 times 6 equals 36. And when we talk about square root of x squared, that's square root of x squared is equal to x, because x times x equals x squared. Notice I didn't put an absolute value, and that's because in the directions, I wrote assume variables represent positive values. That's a very important note, or very important directions. That lets us know that we don't have to worry about the absolute value. That's kind of nice, right? Because it's always complicated. When do I need an absolute value? When do I not need an absolute value? Well, if I put that sentence, assume variables represent positive values, we don't have to worry about it. Pretty cool, right? All right, so the square root of x squared equals x, because x times x is x squared. Square root of x to the 8th is x to the 4th, because x to the fourth times x to the fourth is x to the eighth. We also talked about if the index is not written, it's assumed to be 2, we could just divide 2 into that exponent. So 2 into 8 gives us 4. Or in that first example, 2 into 2 gives us 1. In the last one we have here, 2 into 12 will give you 6. Okay, those are perfect squares, but what about when they're not perfect squares? Well, we could still write it as a product where one of them is a perfect square root, the largest perfect square root. Here's a couple of examples. Square root of x to the fifth. We could separate it as the square root of x to the fourth times the square root of x. The square root of x to the fourth is x squared, and the square root of x just stays the square root of x. The one on the right, the square root of x to the ninth, we could write it as the square root of x to the eighth times the square root of x. Square root of x to the eighth is x to the fourth, and then we still have the square root of x. That's basically method 1. We're rewriting it as a product. But we could do it a little bit differently. We were dividing the exponent inside by the index. Let's look at that last one more time. The index is 2. It's not written, but it's 2. So let's write that 2. Divide 2 into 9. So we're going to divide the index number into the exponent of the variable in the radicand. The quotient, that's the answer, will be the exponent of the variable written in front. The remainder will be the exponent of the variable inside the radical. Okay, so let's divide 2 into 9. 2 into 9 goes 4 times. 2 times 4 is 8. 9 minus 8 is 1, so our remainder is 1. The quotient is 4. So our answer is x to the fourth, and then x to the 1 inside. So go back and read the directions a little bit if you get kind of confused. The quotient, in that case it's 4, will be the exponent of the variable written in front of the radical. The remainder, which is 1, will be the exponent of the variable inside. And then we don't need to write an exponent of 1, so the answer should be just x to the fourth square root of x. So 2 different techniques for simplifying radicals of variables, square roots of variables. Again, to simplify this process, we're going to assume that all variables represent positive values or positive numbers. We don't have to worry about that absolute value. Okay? Okay, let's do a few more. So we're going to divide by 2. So here's our first one, x to the 20th. 2 goes into 20 how many times? 10. Is there a remainder? No. So there's nothing left inside the radical. How about the next one? 2 goes into 15 how many times? 7 times. Is there a remainder? Yes, 1. Okay, part C. 2 goes into 12, and then 2 goes into 18. How many times does 2 go into 12? 6 times. How many times does 2 go into 18? 9 times. There's no remainder in either of them. Part D. 2 goes into 7 3 times with a remainder of 1. 2 goes into 23 11 times with a remainder of 1. When you're dividing by 2, the largest the remainder can be is 1. Okay, now let's put it together. We'll have a coefficient and a variable. So in example 11a, the square root of 16. What is the square root of 16? 4. And then 2 goes into 12 6 times. So 4x to the 6. Okay, these are kind of review problems, but we'll make it more interesting on the next example. How about the next one? Square root of 49, that's 7. And then 2 goes into 16 8 times. Part C, square root of 144. Right, that's 12. And then 2 goes into 12 6 times. 2 goes into 18 9 times. Okay, now the 28. Square root of 28, you could use any method. You could do the tree, which gives you 2 times 2 times 7. And then circle the pair of 2's. So a 2 will go in front, and a 7 will stay inside. And then divide 2 into 13. 2 goes into 13 6 times with 1 left over. Okay, I didn't show a lot of work. I hope it's okay. So again, 28 is 2 times 2 times 7. So there's a pair of 2's, so a 2 will go in front and a 7 will stay inside. Or you could use square root of 4 times square root of 7, and then the square root of 4 is 2. Either method. When you're doing these, do the numbers first, and then leave space for the letters to be written in between. Okay, so when you write the 2 and then the square root 7, leave a space after the 2 so that you can write your x. 2 goes into 13 6 times, so that's why we have x to the 6 in front, and there's a remainder of 1. Okay, part B, square root of 75. Square root of 75, if you use method 1, it's square root of 25 times 3. Or you could use 3 times 5 times 5, so a 5 will be written in front, and a 3 will be written inside. Then divide 2 into 19. 2 into 19 goes 9 times, with 1 left over. You don't have to, but you might want to put a dot in between the last variable, x to the 9th, and the radical. It's just to separate it. Otherwise, if you write the 9 too close, it might look like the index is 9. So you might want to just make sure it's spaced properly. Don't write it too close together. Okay, 80. Method 1 is 16 times 5. Square root of 16 is 4. Or you could write it the prime factorization. There should be 4 2's and a 5. And then divide the exponents by 2. So 4x to the 8th, y to the 5th, times the square root of 5x. Okay, let's talk about perfect cubes this time. So we've talked about cube roots a little bit. Cube root of 8 is 2, because 2 times 2 times 2 is 8. Cube root of negative 8 is also negative 2, because we could have 3 negatives that equal negative 8. So when we look at some examples, the cube root of x to the 3rd is x. We've done this before. The cube root of x to the 6th is x squared. Cube root of x to the 9th is x to the 3rd. And the cube root of x to the 12th is x to the 4th. And the easy way to do it is to divide. The exponent in the answer equals the exponent of the radicand divided by 3. So divide your index into the exponent of our variable inside the radicand, and that'll give you your answer of the exponent of the variable in our answer. Okay, that was a lot of words, right? So now let's talk about when they're not perfect cubes. Again, you can use a combination of methods. It's easier to write it when the first one is a perfect cube. So you want it to be a 6, or a 12, or a 9, or a 3. In this case, we have the cube root of x to the 7th. So we can rewrite that as the cube root of x to the 6th times the cube root of x. Or we have cube root of x to the 23rd. You can write it as the cube root of x to the 21st times the cube root of x squared. I think it's kind of complicated. I think method 2 is easier. Just divide. So we're going to divide the index into the exponent of the variable in the radicand. The quotient will be the exponent of the variable written in front of the radical sign. The remainder will be the exponent of the variable inside the radical. I know sometimes when we give directions, it's so many words, like what? What did you just say? Let's look at some examples. So cube root of x to the 21st. Just divide. 3 into 21. That will be the answer will be the exponent of the variable in front. If there's a remainder, it'll stay inside. So 3 goes into 21 how many times? 7. Is there a remainder? No. How about the next one? 3 into 32. How many times does 3 go into 32? 10 times. Is there a remainder? Yes, 2. So x to the 10th times the cube root of x squared. Don't forget to write your index in the problem. If you forget to write the index, it's technically wrong. So here are just little notes what we did. 32 divided by 3 is 10, and there's a remainder of 2. Now we're going to do the next one. 3 into 12, that's 4. No remainder. 3 into 18, that's 6. No remainder. So x to the 4th, y to the 6th. How about the next one? 3 into 17, 5 times, remainder 2. 3 into 10 is 3, remainder 1. 3 into 12 is 4, no remainder. So the quotient is your exponent of the variable in front, and your remainder is your exponent of the variable inside. Okay, let's put it together with some coefficients. Cube root of 25, that's 5. And then 3 goes into 12 4 times, no remainder. So 5x to the 4th. If you did the tree, there's 3 5s, so you circle the 3 5s. The 5 is running in front, and there's nothing left inside, so that's why there's no radical at the end. How about the next one? Cube root of 40. 40 is 3 2s and a 5. So a 2 is going to be written in front, a 5 will be written inside, and then 3 goes into 19 6 times with 1 left over. So we have a 2 in front, the cube root of 5, inside, 3 goes into 19 6 times, and there's 1 left over. Okay, one more here. Cube root of 108. Let's see, do the tree. There's 9 times 12. 9 is 3 times 3. 12 is 2 times 2 times 3. So you can see we get a 3 cube root of 4. There's 3 3's, 2 2's. A 3 is written in front, 4 inside. And then divide 3 into 18, that gives you 6, no remainder. 3 goes into 11 twice, remainder 2. And 3 goes into 4 one time, remainder 1. Okay, in this example, we're talking about nth roots. In parts A and B, we're talking about fourth roots, and in part C, fifth roots. So we're still going to use the same methods. I think method 2 is easier to find the prime factorization, but you can still separate it into a product where one is a perfect nth root. So in parts A and B, you could write it as a product where one of the numbers is a perfect fourth root and the other one is not. And in part C, you could write it as a product where one of them is a perfect fifth root. I'm going to use the second method where we find the prime factorization and then we circle in groups of n. Okay, so for the 80, find the prime factorization, and you should get 16 times 5, or 4 2's and a 5. If we get 4 2's and a 5, a 2 can come out and a 5 can stay inside. And then divide 4 into 19. 4 goes into 19 4 times with a remainder of 3. So it's x to the fourth in front and then x to the third inside. Notice that I put a dot for multiplication in the middle, and that's just so I could separate it a little bit. If you put it too close, then you're not sure if it's x to the 44th power or the index is 44. So just try to separate it a little bit so you could tell that it's 2x to the fourth times the fourth root of 5x cubed. Okay, now the 48. That's 4 2's and a 3. So you can see that a 2 is going to be written in front and a 3 is going to be written inside. And then divide 4 into 16, which is 4 times. So x to the fourth is written in front. No x is inside. 4 into 23 is 5 times. So y to the fifth in front, 3 inside. Okay, the last one. Find the prime factorization of 96. So how many 2's would that be? That would be 5 2's and a 3. So a 2 can be written in front and a 3 inside. And then 5 goes into 24 times with none left over. 5 goes into 17 3 times with 2 left over. And 5 doesn't go into 3. So you just leave the z to the third alone. Okay, now we'll talk about some fractions. We talked about these fractions earlier, like the square root of 25 over 49. That's equal to 5 sevenths, because 5 sevenths times 5 sevenths is 25 over 49. But we can also think about it as the square root of the numerator over the square root of the denominator. So square root of 25 is 5, square root of 49 is 7. So here's our property. The square root of a over b is equal to the square root of a over the square root of b. as long as b does not equal 0. Or in general, the nth root of a over b is equal to the nth root of a over the nth root of b. Again, as long as b does not equal 0. So we're just saying, work out the top, work out the bottom. Okay, here's a couple of examples. I know it's getting kind of long in the video, but we're getting there. Square root of 12 over 49. So we're going to separate it. Square root of the numerator divided by the square root of the denominator. Square root of 12. You could do either method. 2 times 2 times 3. There's a pair of 2's on top. So a 2 comes out. Or you can rewrite it as square root 4 times square root 3. Your choice. So the square root of 12 would be 2 square root 3, and the square root of 49, right, 7. So that's it. We're just working out the top, and then working out the bottom. Square root of 80 over the square root of 121. The square root of 80, again, I'm not going to show the work, but if you do the tree, you should get 4 2's and a 5. Or if you use method 1, it's square root of 16 times square root of 5. So on the top you should get 4 square root 5, and on the bottom, plain old 11. Square root of 121 is 11. Okay, same thing, a little bit more complicated. We're going to work out the top, work out the bottom. Make sure you pause the video, try to work them out. I think you can. Again, we're going to separate it and then simplify each. So let's work out the top. Square root of 75y to the 11th. 75 is 3 times 5 times 5. So there's a pair of 5s. So 5 will go in front, a 3 will stay inside. And then 2 goes into 11 5 times with 1 left over. In the denominator, square root of 36 is 6. And 2 goes into 4 twice. Okay, same thing with the bottom one. Separate it. And then simplify each one. The bottom is the easiest, right? On the bottom, it's 7y to the 5th. On the top, square root of 27 is 3 times 3 times 3. So there's a pair of 3's. A 3 will be written in front. A 3 will be written inside. And then 2 goes into 14 7 times with none left over. These are cube roots. Same process. We're going to separate it, work out the top, work out the bottom. So cube root of 40 on top, cube root of 27 on the bottom. The cube root of 27, that's a perfect cube, so that'll just be 3 in the denominator. Cube root of 40, we've got to do a little bit of work, right? Do our tree, or write it as a product. If you do the tree, there's 3 2's and a 5. So a 2 will come out and the 5 will stay inside. Okay, this next one has letters, variables. Separate it. The denominator is a perfect cube. That'll be 5y squared. The numerator, let's see, 16. That's 4 2's. 2 times 2 times 2 times 2. So there's a group of 3 2's that we could circle. So a 2 will come in front. A 2 will stay inside. And then 3 goes into 8 twice. So it'll be x squared in front. And there will be a remainder of 2.
Again, you might want to put that dot in between so it doesn't look like x to the 23rd if you write it too close.
Okay, these next two examples, if you notice the denominator is not a perfect square in number 22. In the bottom example, it's also not a perfect square. We're going to use a property that we've been using, but backwards. So instead of separating the numerator and denominator, we could combine it into one fraction. Okay, so here's the note. The denominator is not a perfect square, so it cannot be simplified. However, we can write it as a single fraction and reduce the fraction. Okay, so if we write it as a single fraction, that gives us 24/3. Now we can reduce it. That gives you the square root of 8. Are we done? No, because we could simplify the square root of 8. So simplify the radical expression. Either method, 8 is 2 times 2 times 2. There's 3 2's, so you circle a pair. 1 2 comes out. 1 2 stays in. Okay, you might want to pause the video, try to work out number 23. Same idea. Write it as a single fraction, and then reduce the fraction. Okay, so here it is as a single fraction. Now, can we reduce it? We can. 2 goes into 30, 15 times. And then there's 7 x's on top, 3 in the denominator. So if you use our rule for exponents, you subtract the exponents. 7 minus 3 is 4. And you keep it where it's more, on the top. So that should give us the square root of 15x to the 4th. Now we'll simplify that radical expression. The square root of 15 is 3 times 5. No pairs there, so that stays by itself. Put x to the 4th. There's 2 x's that we can take out. In other words, divide 4 by the index, which is 2. And there's no remainder. So x squared times the square root of 15. All right, our last topic we want to talk about is combining radicals. It's very similar to adding like terms. In both cases, you end up adding the coefficients. For example, 2x plus 4x. You add the coefficients, the numbers in front, 2 plus 4, which is 6, and then attach the variable, x. Same thing with radical terms. 2 square root 3 plus 4 square root 3. Add the 2 and 4 to get 6, and then attach the square root 3. So you can only combine, which means add or subtract radicals, if the radicands are the same and the indexes are the same. So if we have square root 2 plus square root 3, there's nothing that we could do with that. They're not like terms. Since the radicands are different, we're all done. Okay, not too bad, right? Here's example 24, 8 square root 5 minus 12 square root 5. Add the coefficients. Right, that would be negative 4. So the answer is negative 4 square root 5. All right, in example 25, they're not all like terms, but there's a couple pairs of like terms. So we have a couple that have square root 5 and 2 terms that have a square root 10. We can combine those. So if we add the square root 5 terms, we have a 3 square root 5 and a negative 9 square root 5. That will give you negative 6 square root 5. And then a 7 square root 10 plus 4 square root 10, 11 square root 10. There's no rules to say which one should go first. So if you have the 11 square root 10 first, then minus 6 square root 5, that's correct. There's no rules that say which one has to go first. All right, example 26. These are not like terms. They're not like radical terms. However, we could simplify each of them and write them in simplest radical form. So the square root 12, let's simplify that one, and the square root 75, we'll simplify that one. So square root 12 is 2 times 2 times 3. So a 2 will come out, and a 3 stays inside. Square root 75, 5 times 5 times 3. A 5 will come out, a 3 will stay inside. Or you could do method 1. Square root 12 is the same as square root 4 times square root 3. And square root 75 is square root 25 times square root 3. And then simplify each one. 2 square root 3 plus 5 square root 3. Now we can combine those. Now we have like radicals. So that will give us 7 square root 3. Okay, in example 27, there's already a number in front of the radical. So whatever number you bring out when you're simplifying the square root of 18 and the square root of 8, that number will be multiplied by 5 or by 7. So the way it's written, 5 square root 18, it means 5 times square root 18. You just don't put the dot. You could if you want. And the second one is 7 times square root 8. Okay, so square root 18 is 3 square root 2. 18 is 2 times 3 times 3. So there's a pair of 3's, therefore a 3 will come out. 8 is 2 times 2 times 2. So there's a pair of 2's, so a 2 will come out. Now you're going to multiply the 5 times 3, which is 15, and the 7 times 2, which is 14. And then combine the like radicals. 1 square root 2. Usually we don't write the 1, so just square root 2. Okay, almost done. Hang in there. These next two examples are cube roots, very similar though. Let's look at the first term. It's just a 2. There's no simplifying that could go on there. The middle term is this cube root of 16. So if we break that down using either method, if you use method 1, it's 8 times 2. If you use method 2, there's 4 2's. 2 times 2 times 2 times 2. Circling groups of 3, so therefore a 2 could come out and there still be a 2 left inside. And the 54, you could either use 27 times 2, or if you use a prime factorization, it's 2 times 3 times 3 times 3. So therefore a 3 will come out. So the first term doesn't change. The second term, we have the 8 in front, and you bring out a 2, and there's still a 2 left inside. Here I use parentheses. If you want to just use a dot, that's fine. It's totally up to you. In the last term, you could bring out a 3, because there are 3 3's, and then a 2 stays inside. So now multiply the 8 times 2 in the middle term, and the 7 times 3 in the last term. Add your coefficients. 6 plus 16 is 22. 22 minus 21 is 1. So the answer is cube root of 2. Again, we usually don't write that 1. It's like writing 1x. It's just x. Okay, number 29. Same idea. You might want to pause it and work it out on your own. Okay, 24. If you use the prime factorization, there's 3 2's and a 3. So a 2 will come out, a 3 will stay inside. In 81, it's 4 3's, so a 3 will come out and a 3 will stay inside. In the last term, there's nothing you could do, there's just 1 3. So now we'll multiply that. That'll be 10 cube root 3 minus 12 cube root 3 minus cube root 3. You could think of that as a negative 1 in front of that last cube root 3. So 10 minus 12 is negative 2, and then negative 2 minus 1 would be negative 3. So you should get negative 3 cube root 3. Okay, these are the last ones. So notice that the radicands are the same in this problem, but there's also an x in front of each one. Because it's exactly the same, after the coefficients, the 5 and the 8, then we could add them. So if you saw 5x square root 2 plus 8y square root 2, then you cannot add those together. You cannot combine them. Okay, but since they are exactly the same after the coefficients, after the 5, it's x square root 2. After the 8, it's x square root 2. Now we could add those. So 5 plus 8 would be 13. So the answer is 13x square root 2. Okay, our last example. 2x, 5x cubed in the square root plus 9 times 20x to the 5th in the square root. They're not like terms right now, but we're going to simplify each one. Okay, so the first one, the coefficient is a 5 in the radical. Nothing we could do with that. X to the third, the index is 2, so if you divide 2 into 3, we get 1. So 1x could go in front, and then 1x will stay inside. You could also think of it as there's 3 x's, and we're looking for pairs. So if you have 3 x's, there's a pair. And for every pair, one of them will be running in front. So an x will come out, and 1x will still stay inside. In the second radical, there's 5 x's inside. You could either divide it by the index, which is 2. 2 into 5 goes twice. So that'll be your exponent in front, and then the remainder will stay inside. Or you could think of it, there's 5 x's. We're circling pairs of x's. So there will be 2 pairs of x's. Therefore, 2 x's will be running in front, and 1 will stay inside. So this is what we have so far. 2x times x square root 5x plus 9 times 2x squared square root 5x. Now multiply the 2x times the x, that will give us 2x squared square root 5x. And 9 times 2x squared, that's 18x squared square root 5x. After the coefficients, they're exactly the same. Both terms are x squared square root 5x. therefore, we could add the 2 and the 18 to get 20. That was our last problem. The last one's to get a little tricky. I'll see you here for the next one. Bye.